We present our paper on the evaluation of latent-based learning with procedurally generated datasets of shapes. Recently, many methods have been introduced for synthesizing 3D shapes using a latent space to organize the data into small dimensions, allowing for the synthesis of new shapes. Such models typically include both an encoder to encode the input shape and output it as lower dimensional latent space, and a decoder which does the inverse by taking the latent space as input and outputting a reconstruction of the shape. These methods also allow for new shapes to be created through the interpolation between two latent vectors in the latent space. However, most previous work relies on a qualitative evaluation to measure the performance. We instead develop a framework for performing a quantitative evaluation, which uses known semantic attributes of the input shape to compare to. To do so, we create a method that takes these known attributes as input and procedurally generates a set of shapes to use for evaluation. Our procedural generation method is divided into two steps. Our first step uses a split grammar-based approach, in which our pipeline takes in a box as input and then recursively refines it into the desired shape through a set of boxes, which we call our box rules. Our next step can then refine these individual boxes into unique shapes and parts and apply deformations as part of our path rules, which is then outputted as a mesh. Both of our steps uses rules to construct a geometry. We define a rule as a function that takes in a piece of geometry as input and outputs a set of refined geometry. We can then group certain rules together to form a shape, which we call a grammar. We can define which rules to apply for a given shape using an input parameter vector in which each element and its values determine which rule to apply, either as scalar elements or binary ones. For our evaluation, we use a total of 8,800 shapes split into chairs, beds, shelves, and tables. Each dataset includes both the meshes, which are voxelized into 32 cube dimensions, and a set of parameter vectors. We evaluate our experiments on 4 deep learning models, which allow us to encode shapes into latent vectors. In the PGAE, we base the neighbor calculation on the parameter vectors of the shapes. We base our evaluation methods on 2 criteria. The first is the quality of the latent space, in which high-quality spaces better organize the semantic attributes defined by the parameter vectors. The second is evaluating the interpolation quality. In this case, good interpolation capabilities imply that shapes are realistic and smoothly defined between the actual shapes. We can define the semantic similarity of shapes by using their corresponding parameter vectors, in which we compute the Euclidean distances between their parameters. We also apply this method for calculating the similarity between the latent space vectors. We can then evaluate the semantic organization by comparing these distances using the distance correlation. We also evaluate the directions of a latent space in order to assess whether it captures the variation of semantic attributes. For every dimension d in the latent space, we sort the parameter vectors based on the order of dimension d for all shapes. We then compute the total number of changes for each attribute in the parameter sets. Finally, we only count dimensions in which there exist attributes whose total changes are low outliers, which shows a correlation related to the latent dimension's direction. To assess the interpolation quality, we compare the similarity of interpolated shapes to their expected ones. We first construct a set which contains an expected shape and its 2 closest neighbors, determined by scalar attributes in the parameters. We then interpolate between the 2 neighbors in the latent space and compute the Euclidean distance between the interpolated and expected reconstructions. For example, we expect a midpoint interpolation of neighbors with width 0.2 and 0.6 to be similar to the shape with width 0.4. We present improved results from our paper in which our evaluation shows that in general, autoencoders exhibit the same correlation between the semantic parts and the latent space. We also note that the latent space organization can also be demonstrated through our evaluation on the latent space directions, in which the PGAE contains the most meaningful dimensions. Finally, our results for measuring the interpolation quality indicate similar results, both through a quantitative and qualitative measure. In conclusion, we developed a method for the procedural generation of shapes using input parameter vectors that can then be used to evaluate the performance of various autoencoder networks through measuring both their latent space and interpolation capabilities. Our results have indicated that in general, autoencoders have the same degree of performance, with the VAE consistently performing the worst. Thank you for your time.